Hey kids, welcome to section 5.1 probability distributions. Today you're going to learn how to construct a probability distribution for a random variable. So let's talk about what a probability distribution is. Remember that a variable is defined as a characteristic or attribute that can assume different values. So we first learned about variables back in chapter 1, and the variables are the things that you measure. How tall someone is, how many siblings someone has, how many red cars run a light. Those are all things that can be counted and therefore used as variables. Since the variables in this chapter are associated with probability, they are going to be called random variables. So once you use these things that you count in probability experiments, we are going to change their name to random variables. And that's just a variable whose values are determined by chance. And anytime we talk about the chance of things happening, that's probability. And so therefore it's a random variable. Now, there is a difference between discrete variables and continuous variables. We've talked about this in previous chapters. If a variable can assume only a specific number of values, then the variable is called a discrete variable. So, finite number of possible values, or you could continuously count to infinity, but counting just the values. No decimals, no fractions, no anything in between. Variables that can assume all values in the interval between any two given values are called continuous. And so these are things that you measure instead of counting. So if I want to say the length of my shoes, or the length of a kitchen counter, or the height of a chair, these are things that I measure and can have decimal and fractional values. Once we figure out the difference between the two different types of variables, we can create something called a discrete probability distribution. And here is an example of a discrete probability distribution. Notice that we have random variables on top. They are all discrete random variables because they have no decimals or fractions. And then below that are the corresponding probabilities. This is called a probability distribution. Now you can show a probability distribution using a graph or a table. You can also use a formula. And so we're going to learn about all the different types throughout this chapter. So our first example, construct a probability distribution for rolling a single die. So to make a probability distribution, you're essentially going to do like a sideways t-chart. You're going to put the random variable x on the top, and you're going to put the probability of each random variable on the bottom. Now, when you roll a single die, there are 6 sides that can show up. We can see the number 1, the number 2, 3, 4, 5, and 6. These are my random variables. They're discrete, they're countable. Then below them is the probability of each of them happening. So if I roll a single die, the probability it shows up as a 1 is 1/6. The probability it shows up as a 2 is also 1/6. As a 3 is also 1/6. They are all a 1/6 probability of landing that side up. That's a probability distribution. Now, if I want to represent graphically the probability distribution for the sample space for tossing 3 coins, well, that probability distribution is on the previous page. That's the example I gave you right here. So I'm just going to quickly copy it down over here. We're going to put the x on top, the p of x on the bottom, and then we had the random variables 0, 1, 2, and 3. That is awful. 0, 1, 2, and 3. And then we had 1/8, 3/8, 3/8, and 1/8. So this is the probability of flipping a coin 3 times, or flipping 3 coins and seeing how many heads and tails we get. So here's how we represent it graphically. So here we're going to draw what looks to be the start of everything from chapter 2. The random variables are going to go along the horizontal. So we have 0, 1, 2, and 3. These are your random variables x. Then along the vertical, we're going to put the probability of the different random variables occurring. So we have 1/8 and we have 3/8. So I'm just going to count by eighths. So 1/8, 2/8, and 3/8. Now, if you want to, you can simplify your 2/8 down to 1/4. That's your choice. So let's see, the x's were the number of heads. Again, I got that table from the previous slide. And then over here is the probability. Okay, so then we're going to draw bar graphs. Our first random variable 0 goes with the probability of 1/8. I'm going to go up to 1/8, over and down, and notice that my bar straddles my tick mark. Okay, if I do the random variable 1, that one had a probability of 3/8. Random variable 2 also had a probability of 3/8, and 3 had a probability of 1/8. There is your probability distribution graph. You can tell a couple different things. You can tell that it's symmetric. You can tell that the probability of one head or two heads is the exact same. We can also label, I guess, up top here, this is our probability. So instead of x and y, we have x and p of x. All right, let's see another example. This one's about baseball. The Baseball World Series is played by the winner of the National League and that of the American League. The first team to win 4 games wins the World Series. In other words, the series will consist of 4 to 7 games, depending on the individual victories. The data shown consist of 40 World Series events. The number of games played in each series is represented by the variable x. Find the probability p of x for each x. Construct a probability distribution and draw a graph for the data. Okay, so over here we have x standing for the number of games played, and then number of series that played them. So 8 series went to 4 games, 7 series went to 5 games, 9 series went to 6 games, and 16 series went to 7 games. So I need to figure out what the probability of each one is, find the probability p of x for each x. So we're going to do that first. Well, I need to know how many games were played altogether. So if I add this up, I get 40, which is also coincidentally the number I circled in the problem. So to find the probability of playing 4 games, we're going to take the frequency, 8, and divide by the total, 8/40. That gives you 0.2. Then you've got 7 out of 40. If you do this, you get 0.175. If you do 9 over 40, you get 0.225. If you do 16 out of 40, you get 0.4. So we found the probability p of x for each x. Now I need to construct a probability distribution. So that means I need one of these. I'm going to put an x and a p of x. And then I'm going to list my random variables, which are the column 4, 5, 6, and 7. 4, 5, 6, and 7. Then I'm going to put their corresponding probabilities underneath. 0.2, 0.175, 0.225, and 0.4. So there's my probability distribution. Now I need to draw a graph. So now we're going to draw a graph. Along the bottom is going to go my random variables, 4, 5, 6, and 7. This is my x, and this is the number of heads. No, not number of heads. That was the previous problem. Number of series. No, the bottom is number of games. Sorry. Number of games. Duh. All right. Probability wise, we have to go up to 0.4. So let's count by tenths. So 0 0.1, 0 0.2, 0 0.3, and 0 0.4. These are the probability. And these are our P of X's. Okay, so I need 0.2 for going to 4 games. So 20% of the time it went to 4 games. Then we got 17.5% went to 5 games. So I need to go to 17.5. Let's see, let's get these half marks going in here. Okay, so 17.5 is kind of like right here. 0.225. So 22.5% went to 6. Trying to make these bars as close in width as possible, but it's kind of challenging. And then 7 games was 40% time. All right, so we can see that the most frequent was it going to 7 games. We can see that going to 4 games was half as much as going to 7 games. You can see that 5 and 6 were very close in probability. All right. So now that we know how to draw a probability distribution or create one, we need to know what the requirements are just to make sure that we make them correctly. So the first requirement is that the sum of the probabilities of all the events in the sample space must equal 1. That is that the sum of all the P of X's should equal 1. So if I add all the probabilities along the bottom row of the probability distribution, I should get 1. Number 2, the probability of each event in the sample space must be between or equal to 0 and 1. That is, 0 is less than probability of X is less than or equal to 0 and 1. So basically each probability has to be between 0 and 1. So to see if a distribution is a probability distribution, I need to check 2 requirements. So determine whether each distribution is a probability distribution. Well, in letter A, I need to see if all the numbers along the bottom add up to 1. So if I add 1/4, which is 2/8, 2 and 1 is 3, 3 and 3 is 6, 7, 8, looks like it equals 8/8. So the sum of all the probabilities is equal to 1. So that's good. And then I need to make sure that each of the values is between 0 and 1 inclusive. And if you look at all the P of X's, they're all in between 0 and 1. So yes, 0 is less than or equal to P of X is less than or equal to 1. So this is a probability distribution. It satisfies both requirements. Okay, so letter B. When I look, I should be looking at the P of X row. If I add 0.2 plus 0.6 plus 0.1 plus 0.3, I get 8, 9, 10, 11, 12. So I get 1.2. So this is not a probability distribution. So this one is no. The sum of the probabilities is 1.2, not 1. So I don't even have to look to see if each of the probabilities is between 0 and 1 inclusive. I just need to say no because the sum is not 1. Okay, last 2 of these. So determine whether each distribution is a probability distribution. So if I look at letter C, I take a look at the probability. First requirement, do they add to 1? And the answer is yes. 1/4 plus 1/4 plus 1/4 plus 1/4 is 1. So yes, the sum of the probabilities is equal to 1. And then I need to check and see if each of the values is between 0 and 1 inclusive. And the answer is yes. Yes. That's not a y. Yes. Each probability is between 0 and 1 inclusive. So overall, yes, this is a probability distribution. Okay, if I look at letter D, oh, see that probability with the negative? Boom, right away, this tells me no. One of the probabilities is negative. All right, let's do an application problem. This one has to do with dropping college classes. So we're going to look at this table. It lists the different reasons for dropping a college course: too difficult, illness, change in work schedule, change of major, family-related problems, money miscellaneous, and no meaningful reason. Then over here, it lists the frequency with which those different reasons came up. So number 1, what is the variable under study? And is it a random variable? And so the variable under study is what I'm collecting data on, which is the reason for dropping a course. So the variable is the reason for dropping the course, or dropping a college course. Is it a random variable? And the answer is yes. It is a random variable because I can count it and we're using it with probability. So yes, it is a random variable. Okay, number 2, how many people were in the study? Well, I can add up all of my frequencies and I get 144. Number 3 says to complete the table, so I need to go over here and find the percentage for each of these. To find the percentage, I'm going to take the frequency, which is 45, and I'm going to divide by the total, which is 144. So if I do that and round to the nearest percent, I get 31%. Then I get 28%, and then 14%, 10%, 6%, 5%, 4, and 2. And hopefully, if you were to add all of those percentages up, you would hopefully get 100%. There might be some wiggle room, 99 to 101, depending on how your rounding went. Okay, so from the information given, what is the probability that a student will drop a class because of illness? So here's illness. Probability is 0.28. So illness equals 0.28. Then I have because of money, and that's going to be 5%, so 0.05. And then we got last one is change of major. Change of major. Change of major is 10%, so that'd be 0.1. And I guess if we need 3 decimals, because that's what probability is, there you go. Okay, so we continue on. We're still using that probability distribution, or we're still using the table on the previous slide. Would you consider the information in the table to be a probability distribution? Well, remember for probability distribution, everything should add up to 1, and all the values for probability should be between 0 and 1 inclusive. Now, my concern of using this as a probability distribution is there are other reasons that someone may drop a college course. So while this is not itself a probability distribution, we can use it for the purposes that we need it to. So we can say not necessarily is it a probability distribution, but can be used as one. But can be used. If these are the only used as one, if these are the only reasons that we are allowing people to choose from, then yes, it would be a probability distribution. Are the categories mutually exclusive? Can the different categories happen at the same time? And so it looks like from the table that people were only allowed to pick one or the other. In real life, they're not necessarily mutually exclusive. They probably can happen at the same time. You might drop a class because you changed your major and it was too difficult. So the categories are not necessarily mutually exclusive. Not necessarily mutually exclusive. Maybe give yourself an example. Can change majors and be too hard and be too difficult. Difficult. So it's not necessarily mutually exclusive, but I think that they are treating it one when we do these probabilities. But we treated it as if when finding the probabilities. Finding the probabilities. Probabilities. All right, number 7, are the categories independent? That means does one category influence or not influence the others? I'm pretty sure all of the categories are influencing each other, so they are not independent. They are, in fact, dependent on each other. Are the categories exhaustive? Well, it does seem that, there is a miscellaneous column or choice. And so since they have the miscellaneous choice in there, that's kind of everything. So we are going to say, yes, they are exhaustive, meaning every possible answer that someone could think of could be found in one of those. And so then the last question, are the 2 requirements for a probability distribution met? And the answer is yes. All of the probabilities add to 1, and each is between 0 and 1 inclusive. So the sum of all the probabilities is equal to 1, and each of the probabilities is between 0 and 1 inclusive. All right, kids, that's the end of section 5.1. If you guys have any questions, please let me know. And as always, keep calm and keep trucking.